All right, folks, I think we'll get started again. We have our excellent colleague Josh Romero, who's remote on Zoom, who's going to go through the next section on optimizing performance for our NVIDIA GPUs. Really good, useful, practical stuff you'll get out of this. So, Josh, I think you can probably take it away.
Yeah, can you hear me?
Sounds good to me. Everybody in the room can hear Josh okay? All
Yeah.
right. Yeah.
All right, cool. Let's get started. Hi everyone. Happy to join via Zoom today. Last time we did this tutorial, I was in person, so hopefully I can adjust. But so for this section of the tutorial, we'll be talking about optimizing deep learning performance. I'm sharing some slides made by me and my colleague Torsten Kurth, who is a former NERSC member at NVIDIA. This talk here will be mostly focused on single GPU optimization. Later, like kind of later in the tutorial, I guess tomorrow, we'll be covering more multi-GPU content. Um, so let's go ahead. So performance optimization overview. So the reason we're starting with single GPU here is that kind of we didn't really include this roadmap slide that I think we used to in this tutorial, but basically the idea is when you're looking at these deep learning workloads, we kind of like to first focus on making sure your single GPU workload is really, getting the most out of the GPU first before you really start to parallelize, just to make sure you're making kind of optimal use of the resources you have available. So for this performance optimization overview slide or this talk, first we're going to talk about profiling your training code, specifically profiling using NVIDIA Nsight Systems, which is a tool that hopefully most of you have downloaded. And then we're going to talk a bit about how to use something called NVTX annotations in PyTorch to make these profiles a bit more usable or human legible. The middle section of the talk will be focusing on data pipeline optimizations. So obviously with deep learning, most training jobs rely on data, loading data, reading data, training on data. So making sure that your data pipeline is able to keep up with your GPU compute is very important. And then finally, we'll be talking about I guess I will be talking about other ways to improve compute utilization once your data pipeline is working well. So things like mixed precision training, JIT compilation, and CUDA graphs. So first, let's talk about profiling code. So a tool that we make heavy use of in NVIDIA, a lot of engineers working here on these problems, is Nsight Systems. So Nsight Systems is, well, first of all, profiling your code. Profiling is an essential step in optimizing any code in deep learning or HPC or in computing in general. Nsight Systems is a tool that provides a really nice kind of high level timeline overview of your workload and can help you identify bottlenecks. So it can help you identify bottlenecks in your IO or data input pipeline, compute, scheduling, if you're running into unexpected synchronization between kernels or mem copies, things of that nature. So the bottom of this slide shows kind of a generic way you would generate an NSYS profile. NSYS is the executable, profile is a command, -o is an output. In this case, we just called it my profile, and then you just run your Python command. The second command just shows how to limit the tracing to maybe a couple of things to speed up profiling, but also make the profiles smaller. So on the right here is an example of what the Nsight Systems GUI view of a profile looks like. So Nsight Systems can show information about CPU. So this top, depending on how your Nsight Systems was installed and the options you selected, I kind of use the old school view with CPU on top and GPU on bottom. Yours might be reversed. But basically, the GUI window is sort of separated into two sections. There's going to be a CPU section, which is here highlighted in blue. This CPU section will show things like CUDA API calls. So this is the CPU making calls into like CUDA API. So mem copies, launching kernels, calling CUDA device synchronize, and things of that sort. It can show things like OS calls. So if you enable OS runtime profiling, it'll show you things like uh, IOCTL calls to the GPU or different IO operations. If you're really interested in that stuff. And it also can show you, well, those are the things you'll mostly be looking at on the CPU. The GPU section here highlighted in green is what's happening on the GPU. So this is like the GPU perspective of Nsight. So it'll show you things like GPU kernels that are running. So these are, the actual compute blocks that are happening on the GPU, memset, like memcopy operations, and things of that sort. This view provides a ton of information, but can usually benefit from some additional context, right? So if you just looked at this out just as is right now, you might see, oh, there's kind of this repeating pattern. Maybe these are my training steps, but sometimes it's hard to tell. So what we can do is we can add NVTX ranges to annotate these profiles to make them a bit easier to consume. So what an NVTX range looks like in PyTorch, they're basically ways for you to like annotate certain segments of time in the profile to better categorize what's going on. So in this case, it's kind of a stack-based API where you push a range. So in this case, range foo, and then you could pop it off. And when you pop it off, that tells it, to end the range in the profiling. Torch also has this kind of really heavy-handed, but sometimes useful AutoGrad profiler emit NVTX option that we can show. This one sometimes can be really heavy-handed because this will add an NVTX range around every single like PyTorch operation. And sometimes it can really bloat your kernels, but also can make the profiling really expensive. So we don't often use this unless we really need it. This is a really sort of exploded PyTorch training loop that shows how you might want to add these ranges. You would never write a loop like this for input target and enumerate data loader. Well, basically, I've kind of exploded this view to make it a little bit easier to see different things. But the idea here is this AutoGrad profiler emit NVTX can be added as like a context manager around this loop if you want to. But really the idea here is we're just adding these ranges around like step I. So you can see I push step I here, I pop it off at the end. I can push a range around the input target data copy into the GPU. So this is like the data copy range, a zero grad. I mean, you basically can add ranges around whatever you want. Like an optimizer range. You can, in this case, I've added a range around the data load. So I push at the end and pop at the beginning of the loop. And these will just add ranges in those profiles that we can see. So on this next slide, this is what the profile looks like with these ranges added. So you can see compared to the initial slide window, there's these NVTX ranges that got added. These like kind of gray blocks. So with these ranges added, you get a little bit better idea of what's going on, and can identify where you can focus your optimization efforts. So there's like a zoomed in view of a step. So one thing that I like to highlight is, we can see these different steps in the CPU section and the GPU section. So you see at the bottom of the GPU section, there's similar looking ranges, but you can sometimes see that there's discrepancies. So on the CPU, we see the step 18 here, and we see like a step 18 down here. They look different, right? So step 18 in the CPU section says something like it's taking 46 milliseconds and it ends here, whereas the GPU section ends, takes 96 milliseconds and ends like well beyond where the CPU ended. I like to highlight that this is a feature of Nsight systems, is that the GPU range marker will capture like the entire GPU duration of whatever was included in the range. So the CPU time basically just shows how long it would take for you to have launched all these different GPU kernels. The GPU range actually shows how long it took to run all the GPU kernels, if that makes sense. So with this type of profiling in place, you can now more easily digest this sort of profiling view. And we're gonna go through some examples in the hands-on that you can poke around and look at what these mean. But importantly, you're able to identify certain things like, oh, here's this like gap in my GPU compute here. What is that coming from? And so, for example, here we can see, oh, this gap is due to this data load stall, from this range that we added between steps. So we see at some point there's a data load that's taking longer than we want, and it's causing the entire GPU to wait for data to load. So that's kind of the power of this type of timeline profiling tool, Nsight systems. I think we have a lot more time for this talk than we normally do. So I'll pause to see if there are any questions kind of at each major section. So I don't know, Steve, if you want to gauge if there's any question in the room before I move on.
There was one question on the Zoom chat. I don't know if you saw that.
No, I'm not really looking at the chat. So
From Junda, how do I calculate the MFU if I see this profiling information in NV's site?
I don't know. You wouldn't be able to calculate that from this particular plot. So you wouldn't be able to do that.
Okay. Any questions in the room? Nothing at the moment.
Okay. So we'll go ahead and move on to, so in this previous slide, look, we see that, in this kind of sample profile that we're showing, there's a data optimization problem, right? Our data pipeline is slowing us down. And this is actually a pretty common issue that we'd see people run into. They have their training code that they wrote, and they have it on GPU, and they sometimes jump the gun and start doing all the stuff to improve their GPU compute and see no benefit. And it's because their data pipeline is what's slowing them down. So we always encourage people to start by making sure your data pipeline and how you're loading data is as fast as possible so that it can sustain as fast GPU performance as possible. So the next section of this talk talks about data loading optimizations. These are some slides that were generated by my colleague Torsten, which I will present here. He's very much a kind of a PyTorch data loading expert. So for PyTorch, there's a native data loader that maybe a lot of you who use PyTorch are familiar with, PyTorch Dataset, PyTorch Data Loader. Pretty powerful tool, but there are some cons. So the pros to using the regular PyTorch Dataset data loader classes is that they're native to PyTorch, no additional data dependencies. They are flexible, and they're also pretty efficient in the sense that they can spawn multiple worker processes using Python subprocesses, which can allow data loading to happen in the background. That in and of itself is kind of a con. Using multiprocessing to spawn separate workers can cause lots of headaches sometimes relative to using something like threads. Additionally, their data augmentation's not always as great. So if you have certain data loading pipelines that involve a lot of data augmentation like flips and rotations and things that move a lot of data, sometimes these data augmentations, because of multiprocessing, they usually have to happen on the CPU. So if you're doing a lot of like heavy lifting data augmentation, it'd be nice to be able to do those on the GPU in those types of workloads. So one other tool that we suggest to people is NVIDIA DALI. So this is NVIDIA's data loading library. For workloads that really need basically GPU accelerated data augmentation, this is very much the way to go. DALI is very fast. Unlike PyTorch, it actually uses C++ threads to launch all of its workers, so it doesn't have the same limitations to not being able to use the GPU for data augmentation and data manipulation. It has support for some really sophisticated data augmentation, data loading. It can use things like GPU direct storage. It's also framework agnostic. So if you write a pipeline in DALI, it's usually pretty easy to take that data pipeline from PyTorch and run it in MXNet or TensorFlow or a different supported framework. The con of it, though, is that it is, it's its own data pipe, domain specific language. It's got kind of its own way of expressing these data loading operations that PyTorch doesn't. So it takes a little bit of time to get used to. Let me check the time and make sure. Okay. So this is kind of a brief slide that summarizes how you would try and optimize your data loader. There are some native settings in PyTorch for the data loader that you definitely always want to use that are not always the default. So for example, the data loader in PyTorch has a num worker setting. You'll always want to set this to some number greater than 0. If you don't set it to something greater than 0, it won't actually use subprocesses and it won't load samples asynchronously in the background. So I always want to use num workers equal to 1 or greater. The number of which you kind of have to tune, which we will talk about in the hands-on section. Pin memory is a GPU specific option. Basically, this is telling PyTorch to pin the host buffers that it uses that it loads data into for faster host-to-device data transfer. Also allows for asynchronous data transfer. Persistent workers is basically an option that tells the data loader to not destroy and recreate these multi-process workers every epoch. So this just tells them to leave them around. There's really no reason not to leave them running. Just saves time between epochs. The data loader also has some options for writing custom collate functions. So the way the PyTorch data loader works, for those who don't know, is you kind of tell it how to load a single sample in a batch. And it uses these multi-process workers to load each individual batch sample, but then it has to merge them somehow into a single batch. And sometimes that if you know your data set really well and you know that there's like certain optimized ways you could collate and batch the samples together, you can write a custom collate function to do that more efficiently than PyTorch might by default. Additionally, if you have more restrictions on how you need to sample data, there's a custom batch sampler option that enables you to traverse in certain orders, ensure you pick certain samples at different probabilities, things like that. So that's the data loader settings. So this is the actual loading of the data, but there's also data set optimizations you might consider making. These are a bit more advanced, but basically the idea is, make sure you're loading your data as efficiently as possible, whatever data you're loading. So for example, if you're using HDF5 files, there are certain ways to load HDF5 files slow or fast. Make sure you're loading them the fast way. So certain things like if you have, I'll just point out one example here. If you have a really large 3D volume you're loading from, you can use something like mmap to load that, to only load certain chunks of that memory at a time that you might be using for batching or for patching, rather than loading the entire sample at once, and things like that. Okay, that's it on data loader. Those are a couple of pretty abbreviated slides on that, but we'll cover some more on data loader in the hands-on section after this. All right, I'll go ahead and move on unless there are other questions.
Any questions? If you're on Zoom and you have questions, you could raise your hand or probably just go ahead and unmute. It's probably fine. We have one.
Are these slides in GitHub?
Yes. So if we go through these slides fast and you want to review them, all the slides for this entire tutorial are posted on. If you go to the GitHub, there's a section with links that'll tell you. There's a Google Drive folder that has all these presentations, including this one.
Okay. And one question in the room? Yeah, go ahead.
Oh, can you hear me?
Yep.
Perfect. So I have a quick question about the DALL-E. I mean, I think you mentioned that it's very fast and you had everything, yes, in the background. So more specifically about why it's very so fast. I mean, key point why what kind of technology you leverage so that it can be very fast. And then
we're talking about DALL-E specifically.
Yes. Yes.
So I think the thing with DALL-E compared to the PyTorch data loader is that DALL-E was designed to try and kind of maximize prefetch and as much as possible. So they have a lot of really advanced features on how to prefetch data asynchronously, which you don't necessarily get out of the box with the PyTorch data loader. We'll show you an example in the hands-on about where for the tutorial case that we're going to be looking at, DALL-E's not really making a huge difference, which we'll get into, but we can show some places where DALL-E could make a big difference depending on your workload. But basically just DALL-E was designed, I think, with kind of maximum asynchrony and most maximum performance of prefetch to get out of the way of training as much as possible. So it's got kind of some perks there. But the other big thing is that GPU accelerated data augmentation is a pretty big deal. So one limitation of PyTorch multiprocessing is that processes are usually created with a fork. So they fork the process. One limitation of forked processes is that you can't actually run CUDA, you can't run GPU code in the fork process. It's like not allowed by the model. So that limitation on its own already says that the PyTorch data loader datasets cannot actually do anything on the GPU. So if you're doing something, really fancy with your data augmentation that requires like kind of, you really want a lot of memory bandwidth for that. Like let's say you read this NumPy array and you're wanting to do some, I don't know, even something like scaling, right? You have to do that on CPU with the PyTorch data loader, whereas DALL-E can do that on the GPU.
So, so if I understand this correctly, what you said is like, the one key point is DALL-E can do some asynchronous data loading, it's like prefetch data into what's so-called cache, and then whenever we need it, we don't really need to get it from the cache, right? The cache here means the GPU, you allocate some space at GPU, serve as a cache, or actually you put it at the L3 or any other hardware.
So DALL-E can it'll usually just cache data in like GPU HBM, right?
So we allocated some space at HBM.
Yeah, I think you can also cache on the CPU. I mean, basically DALL-E can do things on CPU or GPU. It's very flexible in what it can do. Like it's just a lot more powerful than the PyTorch data loader, but it's also more complicated to use.
Right. So it supports both the traditional cache and then the allocated cache and HBM.
Yeah. Yep. Exactly.
Thank you.
Cool. All right. Let's go ahead and move on. Let's see. Just checking time. All right. So once you have your data loader out of the way, so let's say that you really spent some time optimizing your data loading, and now the data loading is completely behind the GPU compute, and you're no longer bottlenecked by loading JPEG files, for example. That's when you should start focusing on improving your compute efficiency and compute throughput of your model. So one of the first things that we always tell people to try for most networks or most training codes in PyTorch or TensorFlow is to enable mixed precision training. So this used to be a really new and exotic concept, but these days people talk about mixed precision training all the time. FP16 or vFLET16 is not even like cool anymore. People with LLMs are talking about like FP4 and even in lower precision formats. But generally speaking, what mixed precision training is that deep learning models tend to not need a full single precision range and precision to complete training. However, back in the day, it was very complicated to use reduced precision because different parts of training require either more precision and less range, and some parts of training need more range and less precision. So some layers of training are can't handle low precision at all. So what NVIDIA GPUs have are these special hardware units called tensor cores that accelerate lower precision math. So FP16, bFLET16, FP8 and newer hardware. What mixed precision or lower precision, the benefits of lower precision are for math bound operations with like FP16 versus FP32, you can have like an 8 to 16x speed up or even more, depending on how low you go. For memory bound operations, FP16 is half the size of FP32, so you can get almost a 2x speed up just for memory bound operations. You also reduce storage requirements by using FP16 versus FP32. So there are a lot of benefits you get from enabling mixed precision training, but sometimes it's not really tractable to do this on your own manually. So this slide talks about some of the challenges of using FP16. If you just tried to convert a model to FP16 from FP32, it probably wouldn't work. And the reasons are that not all operations are suitable for FP16. So long-running sums with small values, loss functions generally aren't suitable for just a straight application of FP16. And then there's also the vanishing gradient problem where small gradients can be lost to zero and lower precision. So there's usually some gradient scaling that's required. This is for FP16, which has a reduced range. BFloat 16 actually has the range of FP32, so it doesn't actually run into this problem. Applying this can be pretty error prone if you tried to do it yourself. So for a very long time now, NVIDIA has had introduced something called automatic mixed precision in PyTorch and other frameworks, which handles makes using mixed precision easy. It basically automatically handles the conversion of, if you take a model and you pass it into the automatic mixed precision functionalities, it'll automate the conversion of your training graph into a mixed precision graph by taking safe operations and converting those to FP16 where it can, FP16 or BFloat 16. And then for gradients, it'll do automatic loss scaling to keep gradients within a representable range. So this has been available for a really, really long time now, and it's actually just a one-line change or a few line change to enable it in PyTorch. So this is an example of how you would actually do it. Use mixed precision training in PyTorch with a model, and we have this in the hands-on example. The feature in PyTorch is split into two components. It's split into something called a grad scaler, which handles automatic loss scaling and basically updating the scale during training to basically make the gradients as useful as possible. One thing that can happen in mixed precision training is that the gradients can become not representable or not a number. And so the grad scaler will also potentially skip an optimizer step in that scenario, reduce the scale and move on. AutoCast, this line here, is the one that converts model layers to low precision where safe. So it's just a context manager around a model with Torch AMP, CUDA AMP AutoCast around this, automatically converts that to mixed precision. So on Ampere GPUs, like the ones on Perlmutter and newer, there's hardware support for BFloat 16. So as I mentioned before, BFloat 16 is lower precision than FP16. So I mean, it's still 16 bits, but basically what BFloat 16 does is it trades precision for range. So it has the same range as FP16, but it's less precise. The nice thing about that is you don't need to worry about gradient scaling because you don't ever run out of the range of FP32. So when you're running with BFloat 16, which is what a lot of LLMs have historically used, you don't even need grad scaling. So in this case, the example is literally just a one-line Torch CUDA AMP AutoCast. Okay, so that's kind of briefly how you would, add mixed precision training in PyTorch with a few lines of code to improve your compute throughput. So then, we've optimized our data loader, we've added mixed precision training to improve our compute. Now, what do we do? And I always like to remind everybody to not forget about Amdahl's law, which is AMP only speeds up GPU operations. So your overall speed up will still depend on like the total composition of your workload, right? So, if you have math and memory here on the GPU, so this is like math bound and bandwidth bound operations, but you still have maybe some data pipeline operations, or if you're in a multi-GPU setting, communication between GPUs, or communication that might happen on CPU for some reason. That's not going to get sped up by AMP, right? So effectively, you kind of need to do this, in a few iterations. Add AMP, improve your compute. Is your data check, is your data pipeline still fast enough? Because it's possible that your data pipeline might have been fast enough to sustain like a 50% increase in your GPU throughput, but maybe once you added AMP, you increase by 4x. So then go back, check if your data pipeline is fast enough, make some improvements there. If your data pipeline is then faster, see if you can make more improvements to your GPU compute and so on and so forth. And hopefully at the end of this, you'll have a fairly optimized GPU compute pipeline. Okay, so the remainder of the talk before the hands-on is going to focus on some other ways to improve compute in PyTorch that may or may not be relevant to your particular workload, but I still think it's like useful information because some people don't actually know that this is what happens in PyTorch. I'm just going to go ahead and then we can take questions at the end. So one feature of PyTorch that's becoming more and more important these days, it was a bit more niche a few years ago, but now it's kind of core to at least like PyTorch 2.0, is JIT compilation. So JIT compilation is just-in-time compilation. It basically allows PyTorch to analyze your operations and compile kernels on the fly for you. So one thing that I think some people who maybe come into PyTorch like without a lot of experience might not understand is that in PyTorch, every operation on a tensor is a GPU kernel. So for example, you might write like a polynomial on X where X is some torch tensor. So in this case, maybe 2 times X squared. Or in this case, F2 is like a more complicated polynomial, 1/8 times 35x to the fourth minus 30x squared plus 3. Yeah, maybe this is a basis function. I think this is, I can't remember what specific basis function this is, but this looks like a pretty benign line, right? But the problem is this polynomial actually gets expanded out into a bunch of individual kernels and especially if the X, like your tensor is small, very expensive. So the idea is that, in this case, 2 times X squared, there's probably an X times X product kernel, and then another product with 2 or something like that. For this, there's going to be kernels that, multiply X by 35 and subtract and add and all this stuff. And so you can run into 2 issues. One is if X is really small, so in this case, it's 1024 squared, you run into the issue of increased launch latency. So these kernels don't take very long and they don't take a lot of GPU resources to run, but you basically have to wait for them to get launched on the GPU, run for a very minuscule amount of time, launch the next kernel, run for a little bit of time. And that's, a lot of wasted time here between these kernels. If X is really, really large, you still have a problem where you might not have as much launch latency that you've lost, but you're still basically reading and writing X, like this X tensor multiple times. So you're wasting memory bandwidth. So what JIT compilation allows you to do, I guess this slide just covered what I was saying, is that launching numerous small kernels in sequence has performance downsides. You've got this per kernel launch latency that you eat. There's also per operation PyTorch launch latency. So PyTorch itself has some logic and bookkeeping it makes on the CPU before it even launches kernels. And like I was saying before, there's no register reuse between kernel launches using the same data, so you're just wasting memory bandwidth. So just-in-time compilation fixes this because it can perform fusions of pointwise operations like these, and turning these many small kernel launches into one. So before, like I was showing, this first example is 2 kernels. This bottom kernel is, or this bottom function is 7 kernels. If you just add torch JIT script, this actually will compile these into a single kernel, so a 2x squared kernel, like a custom one when it first runs, and it runs in significantly less time. This one's also just a single kernel here. On the next slide, I'll actually zoom in. So this is the kernel to do 2x squared. This is the kernel to do, this polynomial function. And the key point is, sorry, I'm moving this Zoom share bar out of the way so I can see. You can see that this upper function took 10 microseconds to run. This bottom function took 12 microseconds to run. If we looked at the previous slide, we actually see that the top one took 84 microseconds to run, and this bottom one took 406 microseconds to run. So that's a pretty significant speed up just of these 2 functions. So if you have a model, we've seen this before. I think this example really came up in like a graph neural network for like molecular structures. They were doing some kind of basically like a spherical harmonic type fit. So they had these basis functions all over the place. Using this type of compilation can help quite a bit in improving the speed for those kernels. If you're running a more conventional model that's just full of like gems and large monolithic operations. So for example, our vision transformer that we're going to be running here doesn't have a ton of small kernels. It's a lot of really like big gems, big transformers, big attention kernels that are already written. Like it's not as beneficial, but it still can help. In PyTorch 2.0, so a Torch JIT script is the old syntax before PyTorch 2.0 introduced Torch compile, but it effectively operates the same way. And in this case, it's using, whenever I took this profile in these pictures, I used Triton as the backend to compile these kernels. Torch JIT script is in maintenance mode, but it's still available. Okay. Other things to take into consideration when you're looking at JIT compilation in PyTorch is that older PyTorch JIT wouldn't handle dynamic shapes, input shapes. So if for most models that you're running, you usually have a static input shape that you run over and over and over again. But there's some models where the input shape might be dynamic. So in a graph neural network, you might have different graphs with different numbers of nodes, and that changes the size of your input. And you can run the issue where if you pass in dynamic shapes, you actually trigger recompilation every single time, or at a certain point, PyTorch gives up and says, "I can't compile anymore." This is not true in newer PyTorch, but it used to be something you needed to worry about. So in this case, these days, PyTorch can generate kernels that will handle dynamic shapes, which is not in all cases, but in a lot of cases. Additionally, there's certain other fusions other than pointwise fusion that the timer pointwise fusion that you can that PyTorch can do. So in this case, PyTorch can also do reduction fusions. So this is a function here that does like x squared plus y squared, and it does a sum, so kind of like a norm. We see here that PyTorch is actually able to compile through this sum. It compiles it into 2 kernels instead of 4. I think one of them is like a final reduction kernel, but still an interesting feature. Normally, you wouldn't go this granular when you're doing compilations. Like people will just like decorate their model, run with Torch compile, and hope that PyTorch can just compile it for you. But sometimes you might have like individual functions will benefit from JIT that you'll kind of just annotate, and like the way shown in these examples. Here's some links to some more JIT resources you can read if you're interested. And I think the last thing that we'll cover in this last 7 minutes is CUDA graphs in PyTorch. So JIT is one way to tame launch latency in PyTorch. So if you have like a ton of tiny kernels that you're launching in sequence, and you're eating like launch latency costs in between those kernels, JIT will merge those kernels into one launch. So you just have one launch of one giant monolithic kernel. But there are some situations where you have these small kernels that can't be fused. And so CUDA graphs is a feature that basically allows CUDA to record these kernel launch, like all these small kernel launches, into basically memorizes them, memorizes the input pointers, the output pointers, like what memory is input, what memory is output, and the sequence of kernels that you're launching, and actually batches the launch into one kind of monolithic launch of a graph instead of like each individual launch. And so the benefit of this is that you can capture maybe like the forward pass of your model into a graph, and you have one single launch of the entire graph that then kind of more efficiently gets scheduled on the GPU, rather than having the CPU come in every single kernel, like in between every kernel, to figure out what it's doing, launch, figure out what's doing, launch, figure out what's doing, launch. In some ways, this kind of takes like the PyTorch part of the latency out of the way. So this is just kind of an example showing like here's the GPU waiting for work for these tiny kernels, and you can use graphs, and it really compresses all that white space out. I'm not going to go through all of this, just because we're kind of running out of time here and I want to get to the hands-on. But basically, it can be kind of complicated to use graphs. Torch compile now has a feature that'll actually try and capture your model in a graph for you. This example is the like very, very like the manual way of doing it that maybe people wouldn't do these days, but at least it's very like kind of educational. In order to run graphs, you basically have to, like I said, so what a graph does is it records like all the input and output for all kernels into some kind of blob that PyTorch or CUDA can launch. And so the key part of it is that you need to have a static input like entry point and a static like output exit point. So first you have to create these like static input and static label arrays that get recorded in the graph as here are the locations of the input and label go. And like you also have a static output and a static loss that are, compiled like are allocated tensors that need to store the output of the graph. And these have to be fixed because those locations get recorded in the graph. So you create these static input. Basically this slide just kind of goes through everything you need to do, which I'm gonna skip talking about directly. You can go through these slides and read through them, but basically you do a little bit of warm up to make sure that PyTorch is allocated to all the data structures. You instantiate a graph object. You do some stuff with the gradients. You use this context manager to create a graph. So with Torch CUDA graph, you run through your model, and then you can capture the graph, or basically you return the graph and the static input, output, label, and loss entry and exit points. And then the kind of the punchline of all of this is once you've captured this graph, it's just a matter of calling .replay on the graph in PyTorch to launch the entire thing. So you would copy in an input and a label into your static input and static label positions. You call graph replay, which is a single launch that launches everything that was captured in the graph. And then you would grab like the loss or the output out of your static loss and output, static loss and static output tensors. But the main point here is that this graph.replay basically takes PyTorch out of the entire thing, like thinking. It basically just removes PyTorch from it and just says run this sequence of GPU kernels on the GPU. So it's basically as efficient as you can be in terms of launch latency. Let's see. So final remarks here on graphs. I'm just going to skip this slide because I think we only have a couple minutes left. Yep. So here are just a couple of additional tuning tips. Some of these are a little bit outdated, but they're still useful. If you have a model that's using cuDNN, you can enable cuDNN benchmark. This is not default. This allows cuDNN to use like an auto tuner to select like at runtime the fastest kernel. Like it times a bunch of kernels and picks the fastest ones for your model that you're using. This is always a good option to have. On TF32 is I kind of skipped past it in the mixed precision section, but it's a kind of intermediate data format between FP60 and FP32 that is enabled on A100 and newer cards. That gives you some mixed precision benefits just automatically without even needing to use AMP. Fuse optimizers, you should use them when available. They used to be in something called Apex, which was a separate PyTorch module that NVIDIA provided, but now they're a native feature of PyTorch. Basically what fused optimizer means is by default, like the Atom optimizer, for example, in PyTorch will it'll run the optimizer on a per parameter basis. So for each weight you have in your model, it would run an individual kernel to update those weights with the gradients. What the fused optimizer does is it basically says, oh, let me update a chunk of weights at a time with all of its gradients and fewer kernel calls. So again, just to try and limit the amount of latency you have from launching individual kernels. And this is more for image models and CHW versus NHWC, so I won't worry about that for now. But that is all I had on these slides. So I guess we can take some questions, and then after that, we'll move on to the hands-on.
Thanks, Josh. There were a couple questions in Zoom. Maybe we can get to first, and folks in the room and on Zoom can think about their questions. There was one question about whether it's better to use TorchJIT or Torch Compile. Is there any reason these days to use the old?
If Torch Compile doesn't work, I guess. But for the most part, use Torch Compile these days. It's the most supported method. One place where TorchJIT script could come up is like if you're interfacing with a C++ application that ingests like Torch script, then TorchJIT script is useful still. But for most use cases, Torch Compile is going to be where you should go.
Another question was about whether AMP, like PyTorch AMP, supports FP8 on Hopper.
I believe it does, though I would need to check. I'm pretty sure you can set the D type to FP8 on Hopper, it'll work. Whether or not, well, I think it's kind of hard because the thing with FP, so if FP16 mixed precision training is hard, like FP8 training is even harder. In terms of being stable. So I'm actually not sure if AMP supports FP8 because I don't know if it just works. Like if you just apply FP8, it might have the functionality to do it. I'm not sure. I'd have to look. But I know like FP8 is supported for large language models through like something called Transformer Engine in that NVIDIA provides. That does a lot of the like crazy FP8 handling for LLMs. So for example, one complicated thing that comes up with FP8 and LLM training specifically is you sometimes need to use you have to use like a different format of FP8 for like certain kernels and others, like one that uses like one more bit precision versus one more bit Mantissa, and it's like really some pretty smart people that went to and figured out like which version to use, but it's like really complicated stuff. And like it's amazing that it works, but it takes a lot of effort to make sure that you're picking like the right trade-offs between precision and precision and range, but then also there's like certain like scalings that have to happen on a per layer basis with FP8. Like it's crazy stuff. Like you should read about it if you can.
All right. Another question in Zoom.
Talking about for loss function training. Yeah, why not?
Yeah, use it for loss. Yeah.
Yeah, so the question is, can we use Torch Compile for your loss function in training? Like, yeah, actually, I would say that manual application of JIT usually was for loss function. So someone would have like a complicated loss function and they wanted to compile it into a single kernel. You would use Torch Compile or JIT script.
And I think we apply it on the loss function in the example today,
Yeah.
right? Yeah.
Yeah.
And then I guess you can see the questions. Do you see
Yeah,
them?
yeah, I'm looking at the chat now. So are most of the tips applicable to TensorFlow Keras, or is it easier to transition to PyTorch? So some of them are. We've tried to label things that are PyTorch specific optimizations in, so like this last slide that we're on is PyTorch specific. AMP, like the automatic mixed precision stuff, is available in TensorFlow and Keras. The syntax will look a little different. CUDA graph support, I don't know what the state of that is in TensorFlow or Keras, so that's probably PyTorch specific. As I just generally say, like these days, a lot of at least engineering work, like I feel like a lot of people use PyTorch, and I think a lot of the optimizations, a lot of the LLM training stuff that NVIDIA generates these days is mostly in PyTorch. Okay. So I think with that, maybe we should move on to the hands-on.
Yeah, well, we maybe give folks in the room a chance. Does anybody here have a question? Okay. Yeah.
I just ask one quick question. So I was wondering how efficient the garbage collection, the CUDA garbage collection for GPU memory could be, or how bad it could be, because garbage collection is famous for bad performance for many areas. So
how efficient
the 100 and large scale computation with.
Well, so it's so garbage collection is a Python feature, right?
But it's still based on CUDA, right?
No. So if you're running a PyTorch workload and you're thinking about garbage collection, what garbage collection means there is PyTorch deletes tensors, and then that frees CUDA memory. So the garbage collection itself is not like a GPU feature, right?
Okay, so it's nothing about just
No, like yeah, you're basically controlling when PyTorch deletes stale Python objects. And those Python objects in PyTorch are tensors, which may or may not hold on to GPU memory. And so when the garbage collection is deleting PyTorch stuff, which then is freeing GPU resources. So I don't know what the question is about, like efficiency. I guess it's
so it's nothing about CUDA.
Yeah, I mean it's not a CUDA feature, right? I mean it's you might need to run the garbage collector sometimes manually because just the nature of Python is that sometimes you have objects that hang around longer than you want them to. And if you're running deep learning models that are like really straining memory resources on the GPU, you can sometimes manually call the garbage collector in Python to clear out as many unused PyTorch tensors as you can to free up GPU memory so you don't like run out of it. If that makes sense.